This video is a guide to combining the equations for kinetic, elastic potential, and gravitational potential stores in order to calculate a missing variable. So for instance, I can use the kinetic equation and the gravitational potential equation to calculate the velocity of a ball if I know how far it has fallen. Similarly, if I know the spring constant of a bow and arrow, and I know how far that bow and arrow is stretched, and finally I know the mass of the arrow, I can use that information to calculate the velocity of that arrow by using the elastic potential equation and the kinetic equation. So let's start by looking at the equations we need to know. We have elastic potential, E is equal to a half KE squared, where K is the spring constant and E is the extension. We have kinetic, which is EK equals a half mv squared, where m is the mass of the object and v is the velocity. And finally we have gravitational potential, where delta Eg, which is the change in gravitational potential, is equal to mg delta h, where m is the mass of the object, g is the gravitational field strength, which on Earth is 9.8 newtons per kilogram, and delta h is the change in height. So we must also remind ourselves of the law of conservation of energy. Energy can never be created or destroyed. It can only be transferred from one energy store into another. Now in all of these cases we are assuming closed, isolated systems where there is a perfect energy transfer, where all of the energy from one store goes into the intended store. So let's consider our roller coaster. A roller coaster cart of mass 300 kilograms starts at rest at point A. At rest simply means not moving. It then travels along the track to point B. Assuming the weight and normal contact force are the only forces acting on the cart, calculate the velocity of the cart at point B. Now this has given us enough information to calculate the velocity. So first of all, conservation of energy. We need to know that the start has a gravitational potential store, and the end there is a kinetic store. So we're going to need to use the gravitational potential equation and the kinetic equation. So since it's a perfect energy transfer, we have that the energy in the kinetic store is equal to the energy in the gravitational potential store. Once we have that, we can replace EK and delta Eg with their equations. So we have a half mv squared equals to mg delta h. Now that we have that, we can use the numbers we've been given in the question. So we know the mass of the cart is 300 kilograms, so m is going to be replaced by 300. We also know that the change in height, delta h, is 10 meters. And finally, we know that the gravitational field strength is 9.8. Once we've worked out all of those numbers, we can plug them in. This is substitution. So we now have a half times 300 times v squared equals 300 times 9.8 times 10. You'll notice v squared is the only variable left. So once we've done that, we have 150 v squared is equal to 29,400. So now that we have v squared next to 150, we need to get rid of the 150, so we divide both sides by 150. That gives us that v squared is equal to 196. And if you know your square numbers, you'll know that that means v, the square root of 196, is 14 meters per second. Next, a bow with a spring constant of 400 newtons per meter is stretched 0.5 meters. An arrow of mass 0.1 kilograms is released from the bow. Calculate the velocity of the arrow. In this case, at the start, we have an elastic potential store of the bow, and at the end, we have a kinetic store of the arrow. So we're going to need to use the elastic potential equation and the kinetic equation. So again, a perfect energy transfer means all of the energy in the kinetic store will go into the elastic store, or vice versa. So we have a half mv squared equals a half ke squared. Now, we have the mass of the arrow, which is 0.1 kilograms, so m can be replaced by 0.1. We have k, which is 400 newtons per meter, and we have e, the extension, which is 0.5 meters. We substitute in the numbers, and we have a half times 0.1 times v squared equals a half times 400 times 0.5 squared. We're going to solve for each side, so we end up with 0.05 v squared equals 50. Now we need to get rid of the term 0.05 from the v squared, so we will divide both sides. We'll perform the inverse operation. Once we divide both sides by 0.05, we find that v squared is equal to 1000. Once we square root the v squared and the 1000, that gives us v is equal to 31.6. That will be meters per second. Now, since we do not have that many significant figures in the question, in fact the smallest number of significant figures we have is 1, we're going to round this to one significant figure, giving us the answer is approximately 30 meters per second.